Vineet Singh. Professor Vineet Singh is a professor of the Department of Mathematical Sciences at Indian Institute of Technology, PhD, Varanasi. Specialization are numerical analysis, computational methods for integral and differential equations, fractional calculus, mathematical biology. He completed his PhD degree from IQAC. That time it was not IQ. Then it was IQAC. Present it is from 2012 it is IQAC. Then he did postdoc from Russia. Then came back and joined in NIT. Yeah. Then West Pilani Goa campus. Then came to our institute. And he has, I think, near about 100 publications for not written there. Dozen of aegis scholars he has supervised, and also more than 15 has produced index on his students. He received the boycott of fellowship, and that time it was very hard to get. And he is the president of faculty forum of IIT-BH. Very prestigious IIT-BH. And he has visited a number of countries, a number of workshops. So today's talk is approximation of generalized time fraction derivative and its application. I think we will this lecture.
Okay, thank you. So, thank you, Professor Suvidas. So, fine, I have this. So, first of all, I would like to thanks to the Dr. Subham for his invitation, and also thanks to Professor Suvidas to motivated me to join this conference. And basically, during this presentation, I am going to more focus about approximation of generalized time fractional derivative and its application. This work is already have been published in one of the best journal of the Q1 journal, and with my PhD student Vikas Sharma. This is a recent work, so that's why I chosen this work to share with all of you, so that I can get some feedback or motivation to improve some work also. Because in conference, usually we are going to get some motivation, some ideas from the participants, from the faculty members, from the professors, so that we can improve ourselves. Okay, so as Professor Subidas lecture he mentioned that nowadays many people are working in the area of fractional derivatives. So this is attracting more to the applied people, those who are working in the applied area. So nowadays there is a lot of application also. We can find out many application. I will show the introduction part as well. In the introduction part, I have mentioned many application part as well. How many applications we have nowadays people are doing. So basically, as Das sir told that means there is some problem related to geometric interpretation. The people are raising the concerns that why you working on fractional derivative and what is the geometrical interpretation. So geometrical interpretation, in some sense, I can say, suppose you have function y equal to x square, and you would like to suppose differentiate one time. So y equal to x square representing the shape of parabola. So when you differentiate, you will get straight line 2x. Okay, the normal derivative, ordinary derivative. But if you do the fractional derivative, it will provide you the information or intermediate information. What is going on between x square to 2x? What is the shape of the curve? Shape is not directly going to bend up to x square. That shape is to be the straight line. There is an intermediate step. So when you apply the fractional derivative, then you can see the beauty of that intermediate step, how this picture will come, how this orientation will come to achieve the shape of x square, that shape, curve shape to a straight line. So that information you can capture through this. So meanwhile, I can say that these are the examples we can give to convince those who are talking about the geometrical interpretation. This is very basic we can give. Anyhow, so just I am going to give now my basic what we have done in this work. So these talk outline are based on motivation, then novel research for generalized time fractional derivative, physical applications, and then contribution and future scope. So what I have done in this presentation in this work, I first time, as per literature review, first time we derived the approximation of the capto derivative, generalized capto derivative, uh, up to the means order, whatever the order you need. Suppose if you approximating the any function, then there is a two term will come, convergence and order of convergence. Okay. So first time literature we are established, we designed the approximation of the generalized capto derivative up to the order as per our choice. Like in the numerical integration, there is formula. Numerical integration, trapezoidal rule, Simpson's rule, method of undetermined. The method of undetermined will give you the idea how much accuracy you need. Just give me the accuracy, how much accuracy you need. That method will provide you. Okay. Simpson's rule and the one third and three rule is no, where there is some limitation. But when you work for the, when I'll say no, I need accuracy up to 10 to the power minus 5 or second order accuracy up to 10-degree accuracy. So method of undetermined will provide you. Then this idea motivated me to design the approximation of the capto derivative, which will give the order of accuracy as per your choice, whatever the your choice we have. But that approximation is basically based on the Lagrangian approximation. So what is the Lagrangian approximation? You can approximate a function. If function is continuous on the closed domain, and then we can approximate by the polynomial by Strauss. That idea will provide you the information how to design the approximation. So basically, what I have done, just I am going to focus on that. What I contributed, what we contributed, not I, we contributed in this work. So we contributed, we designed the one best approximation for generalized capto derivative. I'll show the what is the generalized capto derivative, and we received the order like up to 5 minus alpha to 6 minus alpha, which was not earlier was attempted. It was only the 4 minus alpha maximum by the many mathematicians, but we tried our best to find out the best accuracy, best order of conversion. And then we implemented, and then we have proven many results, many properties. So just I'm going to focus on that. So as I told you that introduction part attracted many mathematicians to work in this area because it has lot of application. You can see in the Newtonian fluid and viscoelasticity and other area, it has many applications. So those who are interested for the application, they may go and see the references 2, 3, and 4 and 1. Okay, so we can find many application for that. So basically, just this is a generalized time fractional derivative. So what is the beauty of this operator? This is the operator. So the beauty of this operator, there is in the fractional derivative there are three major operators. Like Professor Vineet lecture, he explained there are two operators: Riemann-Lewis and capto derivative. So this is a generalized capto derivative. So through this we can find the all the capto derivative format. Okay. So what is the use of, what is the beauty of this? The beauty of this operator is we can find what is the use of the scale function. There is a scale function. Increasing new function is a scale function, and mu is the weight function. What is the role of this? The role of this is, suppose if you use the capto derivative operator and you wish to find the information about between 0 to 1, between time 0 to 1. So what is the role of scale? Scale will give you the information about A to B interval. If you know the 0 to 1, then we can use the scale function, and that scale function will give you the information about any interval A comma B. So that is the beauty of this operator, that if you wish to find the information along any time interval, through this scaling function we can find out. That is the beauty of this operator. Okay. So the problem is how to approximate this integral. That integral, how to approximate. I think it's not working on the this screen. Yeah, yeah. So okay, it's fine. So just I'm going to yeah. Yes, due to a picture, yeah, it's okay. So look here, I as you say, scale function and weight function is providing a framework for this approximation. So I just more focus on the scale, how to handle the scale function. So what I have done in this approximation, I school use the scale function, and I have written, we designed the approximation based on the scale function. We have proposed the Lagrangian approximation. Okay, we have proposed the Lagrangian approximation with respect to scale function. Okay, so how do we do this? So these are the content which are related to this. I'm not going to read this. As I told you, this will give you the many classification, like Riemann-Lewis capto derivative. If you take mu is something and nu is what t, there are many derivative we can define by one single operator. So that is the beauty of generalized operator, that we can define all these operators by using the one single operator, by taking the many different types of scale function and weight function. Okay. So just sorry. Okay, you can. But okay, present. It's fine. Okay. So what is the research gap? If you do any numerical approximation, any numerical analysis, any research work, first we need to find out the research gap. So we do the literature survey and then we found that these are the research gap. Alikno in reference number 6 is produced his designed L21 sigma scheme which provided the information about the order up to 3 minus alpha when alpha is 0 to 1. Then Maurya et al., this is my student, he has proposed one scheme which I have given the order 2 minus alpha and 3 minus alpha of when alpha is 0 to 1. And then you et al. In 8-9, he also proposed by using different weight and scale function. Okay. So these are the scale function. You have seen that order is up to maximum 3 minus alpha and something. Okay. Like in 10 also we have proposed 4 minus alpha. Then we think, can we improve the order as per our choice? That was the idea behind this work. Can we improve the order of accuracy or order of convergence as per our choice? So as up to some limitation we can do. What is the limitation? Why the limitation? I am using the term limitation. There is some reason. You know, if you do the approximation by Lagrangian polynomial, the Lagrangian polynomial also have the limitation. If you take any polynomial of degree 10, 5, and if you wish to approximate, you cannot find degree of precision up to 10 degree and 20 degree. There is some limitation of Lagrangian polynomial as well. Due to this limitation, our scheme, proposed scheme, also have some limitation. I will come to this topic later. So what is the highlight of the work? As you say that this is a very novel approximation. And one beauty of this approximation that we have developed this, we have designed this approximation for both types of solution, smooth and non-smooth. Okay. But we have chosen only uniform discretization. So, you know, if you do the discretization of the time, first what we have done, we have taken the time domain 0 to t, and then we try to discretize the domain uniformly. That there is two or three types of discretization. Maybe you can do adaptive graded mesh design, non-uniform discretization, or adaptive mesh. You can choose adaptive mesh as well. But in this problem, we have chosen uniform grading to find out the approximation of this operator. Okay. So these are the details about the highlight of the work. So approximation procedure. As I told, I'm just going to just discretize the domain by uniformly. Uniformly means step size is fixed. Okay. So these are the approximation. So now we this is the operator. So we can write this approximation like 0 t naught to this is a tk. So just we are writing in terms of summation t naught to t1, then t1 to t2, something like that in form of summation. Okay. And we have chosen that gt is mu of t and gt, and mu of a is 0. Okay, this is mu and this is mu of a is 0. So this is going to be like some notation I have used here. I have used that scaling function should be 0 at a. That is the property we have chosen. So look here. So what is the procedure? So we have given the name of this scheme ln scheme. So what is the meaning of ln? Ln means if you choose n is 2, so that scheme is known as L2. That L2 means doesn't mean that standard L2. That L2 means we have to fit the approximation of Lagrangian polynomial t naught to t1 is linear, and onwards this we have fitted what? Quadratic. Means we have fitted the Lagrangian polynomial, linear Lagrangian polynomial t naught to t1, and onwards t1 we have fixed quadratic. So you know the for quadratic how many points you need? 3 points. So likewise we have done the procedure. Then I am coming to the case when n is 3. This is the idea behind the to getting the higher order of accuracy for the proposed scheme. What is the n is equal to 3? N is equal to 3 means our scheme name is L3. So L3 means we fitted first linear, then quadratic, and then onwards this we have fitted cubic, 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 cubic. So that idea we have proposed first time to see what will happen and what will be the accuracy, what will be the order of convergence. So that idea enhance the order of accuracy up to our choice. And we have received numerically up to 6 minus alpha. Then we can say why up to 6 minus alpha, why not 7 minus alpha? So due to this limitations of approximation behavior of Lagrangian polynomial, our scheme also have some limitations. Okay. So now if you take n is equal to 4, so how are you going to fit linear, quadratic, cubic, and then onwards biquadratic, means 4 degree polynomial. So that idea we have proposed, very simple idea of approximation, and that simple idea is given one nice approximation of the generalized capital derivative. Okay. So those who are working in that area, they may get connection that how to do such types of work. That was the motivation behind to give the talk. So as I said that linear interpolation, how to do. So if you do the linear interpolation, this you're doing with respect to this function, scaling function. So that's why this is going to be useful with respect to scale function. As I said that scale function have the behavior to shift the time interval from 0 to 1 to 1 to 2 or 2 to 3. The beauty is only due to this, because you have chosen the approximation with respect to what? Scale function. We finding the approximation of Lagrangian polynomial with respect to scale function. So that is the simple approximation of Lagrangian interpolation. And then what we have done, we have approximated whatever the operator I have defined. I approximated tj minus 1 to tj, and then I replace this value by derivative of this term. Sorry. Okay, just wait. Okay. Yeah, so this is a linear approximation. So I just replace derivative of this term by here, and then I try to solve this integral, and that integral have analytical solution, not numerically. So we have solved this integral, and then we receive the closed form in terms of series. So when we approximate, so look, we have here coefficient, this coefficient. So this coefficient is going to play a important role to handle the order of convergence of this approximation. When you do the approximation, if you are doing in the area of numerical analysis, there are two concerns. The one is convergence, and second condition is what is the order of convergence. So order will give you the how much faster the scheme is faster. So for that purpose, that coefficient which I have mentioned, that coefficient is going to play a role. This coefficient has the beauty. If you take the summation of this coefficient, it's going to be, I think, 0. I think, yeah, it's going to be 0. I will show this later. So these are the coefficient. Okay. For quadratic interpolation, same process we have to do. We have to choose the quadratic interpolating polynomial. Then we fitted in the whatever we have the operator. In the operator, we have replaced the GT, whatever the GT we have inside, and we replace that GT by this approximation. We have done calculation. Again, we have received the approximation of this operator in terms of discrete form, and this is coefficient. Okay. So I'll show you later on the more general form. These are the coefficient. So there are two cases. Okay. When you do the approximation, there are two cases will come. Suppose we have only suppose you choose an n is 2. So if you choose an n is 2, so means L2. So L2 means we have to fit linear and quadratic. So how many interval you need at least? Linear means T0, T1, and then needs some more points. So means if number of sub interval is less than the degree of polynomial, so then there will be problem. But when n is, suppose n is 2 and number of sub interval is larger, like 3 and something, in that case we can fit this. We can fit if we have linear, quadratic, 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 we can fix linear, quadratic, cubic, cubic. So there is some restrictions. If number of interval is not best fitted, then in that case there will be problem. So we divided the, when n is suppose 2 and suppose this j is suppose this j is greater than n is 2 and j is 3, then this way you have to do the approximation. Okay, there are two. When j is less than j means number of time interval, how many sub interval you have chosen. If number of sub interval is greater than number of degree whatever we have fixed, n is 2, so number of sub interval is more than 2, okay, then we can take this approximation. If n is 2 and suppose j is 1, then that scheme, that approximation will not work as by case 1, that is going to be case 2. Okay, so we just we divided for simplicity in two cases, and these are the approximation. 2.3 is the approximation in that case, and these are the coefficient. We just manage the coefficient. This coefficient we writing in terms of this parameter. These are the coefficients, because this coefficient is going to play a role to find out the stability. So look, likewise, I'm moving forward. Case 2, as I said, when j is less than n. Suppose j is 2 and n is suppose 3. Okay, so there will be problem. So we have to handle like this. So this is case 2. For that case, we have to handle approximation in different way. So we just we have divided in two cases, and then we approximated this, and then later on we merge the both cases to find out the one approximation. Okay, so later on what we have done, this matrix, look, this is matrix. This matrix is related to the coefficient which I displayed there, that what coefficient is going to play important role. So that coefficient matrix I have represented in terms of mkn, and this is the akl is this matrix, and this is the nth approximation matrix. So this simply I can say these are the coefficient matrices. Okay, means all the coefficient we can write in terms of matrices, and then we can do some simulation. Okay, so just I am coming to the case for k less than 1. I'll say k is less than means j, that is k is related to j, so k is less than n, then that is the approximation. Okay, so finally the error term, when you do the approximation, error is important. So we have proven the error. What is the bound of the error also in this case? We have proven that when you have designed, when we designed the approximation by the both cases, we have proven that error is bounded. Okay, these are the result for this case. And as I said, the coefficient, whatever the coefficient we have, that coefficient summation should be always 0. And that is the beauty of this approximation, that terms will help you to prove the stability. To prove the stability of the approximation, we required that condition, otherwise there will be problem. Because there are many types of stability we can prove. If all the coefficient are increasing, some sense increasing or decreasing, but here the coefficient do not have behavior like only increasing and decreasing, sometime increasing, sometime decreasing. Then we have chosen the second, third path. If suppose summation is 0, okay, so in that case we have proven the stability, because the coefficients sometimes have negative terms, sometimes have positive terms, so we could not establish the increasing and decreasing behavior of the coefficient. The many authors have used the concept to prove the stability by using increasing and decreasing concept about the coefficient, but we have chosen some different structure, different framework to prove the stability, that is the summation should be 0, and we have used this to prove the stability. Okay, so if gt is 1, what will happen? So I just proven this result. If gt is 1, then we have proven that this result, whatever we have approximated, I told this is value is this one. So I just shown that if gt is 1, then we have shown that this is equal to 0, because it is going, gp is going to be 1, and that in this case that summation is equal to 0, and this term will be never 0. So we have proven this is a case when gt is 1, then we have proven that that summation is 0 in the case of gt is 1. Very simple logic we have given, and likewise we can do for other function if gt is some function. Okay, and numerical validations. So we have established both the properties. The first property is theoretically we proven the order of convergence. Whatever we proven the theoretically order of convergence, we have validated our result numerically as well. Sometime I have seen many papers you can find in the, you can search, they have given order of convergence 5, 6, 7, 8 something, but theoretically they have not given the result. Okay, but in this work we have proven if order is 5 minus alpha, theoretically, numerically also established the same. There is no deviation. There may be minor deviation in terms of integer, some 0.01 some derivation, like some deviation may be due to computational cost, due to efficiency of our system. If your system is very good, if perfect, if you do calculation on high better workstation, then your accuracy may be matched, but there is very minor changes due to computational cost. Okay, so error analysis, we have done the error analysis of this approximation as well, and we have proven there are some property As we say, if the scale function is GT, then computational accuracy will be exact. We have proven this numerically. How we have proven numerically? This is example where the we have chosen a scale function. This is a scale function. If a scale function equal to this GT, and then we can show that this is the exact solution, and numerically also establish this is true, because error is 10 power minus 14 means that is going to be accurate to what? 0 in some sense. So we establish these result, and we have first time established such types of result for generalized capital derivative. That if these things happen, that is the case. Okay. So okay. So these are the case if GT is T power A and a weight function and scale function as T power C and T power B. Then we have established the error bound with respect to power A and B and C. We have established the relationship between the degree of the polynomial of GT and whatever mu and T and mu and nu have. Then we have established the relationship. First time we have established the relationship with respect to error bound as well. We have proven the error. If this A have relation KB, then we have proven bound will be like this. We have proven if for a smooth case, error bound will be this, and this is the error bound. For non-smooth case, we have proven this error. So means we have established for the proposed approximation, the error bound is also have the variation with respect to the function. If function is solution is smooth, if solution doesn't smooth, if solution is non-smooth. Also we have provided the information, we designed the error approximation which established theoretically as well as numerically also. Now the similarly we have chosen some other relationship. Similarly means these you can see this is for non-smooth case, and for sufficiently smooth case we have established some result. These are the result related to simply approximation of generalized capital derivative till here. Okay. Now I am moving towards, there are many examples I have proposed where we have established the whatever the order of convergence we are getting theoretically, numerically also establishing the same. Okay. Now I am coming to the case, other cases, because due to time permit I have to move forward. I am coming to the application part. So look, what I have done to test the approximation, we have chosen model 3.1, very well known model. You can find thousands of the paper based on this equation. Okay, general time fractional diffusion equation. So as Dasar also has given today presentation similar like some operator. Yeah, so this is a generalized case. This I think in your case this was the capital derivative. I have chosen here generalized capital derivative, and we have proven here the for this model what we have done. We have established a approximation of this model. We have established that whatever the approximation has come, whatever we designed, that is going to be order 5 minus alpha or something better than the existing scheme, and we have proven convergence as well. And I will show by the graphically also what is the accuracy of this proposed model. If you simply replace this operator by the whatever we have designed, the operator, the discrete form we have designed, if you replace by that, only left hand part if you replace by that, and right hand side I have central difference operator and then compact operator. Okay. So what we will get, I'm not going to read all these things. So this is basic definition about existence of the solution of 3.1. What is the minimum condition should be there on the G1, G2 and G3 and Fx. We have proposed this to existence and uniqueness solution. Okay. So just I am coming to the look 3.2. So 3.2 I have just proposed, I replace this by 3.2 which we have designed. Okay, earlier I told you also. And then we have used that space derivative by using this, and we have used this operator, compact difference operator, both side of the model, and then we have proposed the new order of convergence. Okay. So if you do like this, finally I am coming to the scheme. Look the scheme how it look like. This is a finally scheme 3.7. So what we have done, we have simply approximated the time derivative by the proposed approximation and space by the compact difference operator, and then we merge it. Then after merging this, we have received 3.7 is the system of equation. So in the system of equation, the matrix property is very important to prove the convergence and uniqueness. So if matrix, there is a scheme, Gauss-Seidel scheme, Ax equal to B, you can write x equal to bx plus c, and the norm of b less than 1. if B matrix is tridiagonal matrix, there are many properties of numerical. All of you, those who have done numerical analysis, how to prove Gauss-Seidel and Gauss-Jacobi method will converge and order of accuracy, whatever. So we have done the same things to establish this convergence and other behaviors. So just I am coming to the as a 3.7 passes a unique solution. We have proposed 3.2 to find the order of computational scheme, as you say, tau for rho n plus h4. So this I told you, this is going to be 5 minus alpha, sometimes 6 minus alpha as well. Okay, I'll show you numerically. We have proven that solution computationally scheme is bounded by this. We have proven that bound is bounded by initial condition. And these are the example. And to test our result, as I showed, that this scheme, if you use here, use n is 2. So n is 2 means we have to put linear and quadratic element 2 scheme. So element 2 scheme is will give 3 minus alpha. Okay, this is our proposed scheme. This is better than this one. Now, if you go to the other model, if you take n is 3, I will come. Okay, just so through this graph, I am going to conclude my talk. When n is 1, linear approximation, order is minus 3, means linear. I fit the linear in the entire interval. When n is 2, I fit the linear, then quadratic, then the error will be minus 5. Look, the error is improved. When n is 3, so we fitted linear, quadratic, and then onwards cubic, cubic, cubic. So if you do like this, the accuracy will be minus 7. And if you do n is 4, then 10 is for minus 9. So if you look this graph, all the 4 graphs, we can see the behavior of the approximation with respect to n. Means n is increasing, then accordingly the error is going to be more accurate. Okay. So these are the structure of the designed approximation. It's shown that the approximation is really better than the other existing scheme till now for the generalized capital derivative. So these are the major contribution which we have contributed. We have shown stability and other behavior. We have done deep numerical analysis for this proposed algorithm. We have established the algorithm as well. And this paper is recently published based on this idea with my PhD student. And okay, so these are the differences. Thank you.
Great that how the numerical method is so powerful to calculate the fractional linear equation.
Linear model. In future scope, I have mentioned for non-linear, for non-uniform, by using adaptive grading, we have submitted the second version of this in the same journal. Yeah.
For the young researcher or young people, that if you motivate this area, because we it is a time to end, and the people have to start. So, so it is like mod function. एक खत्म हो जाता है और एक बढ़ जाता है. So, so you should come forward. This is a very booming area. And another thing is that sometimes we say, put up the switch, put on the switch. So what is in between? So that is the question what we are saying. And sometimes it happens that if you have the idea of automation theory of computation, you see that some automation machine deterministic sapling but non-deterministic they do not allow. So what you have to do, you have to convert NFA to DFA, then you have to apply to the Turing machine. So in this way, in between, what is in between? So the function and the value. What is in between? And if you have any questions, especially the young people, any question? Yeah. Just out of curiosity, like you said, we can do fitting in such a way that linear, quadratic, cubic, and so on. So can we switch it? Yeah. Cubic?
In some sense. There is like I told you there is a reference. He's given L1 to scheme and L2 one sigma scheme. So he just switched and then he found that order is improved in some sense. So he set up something, but in my case, if you do, there is some difficulty will come because if it a linear quantity, in our case, the degree is going to improve more and more. Okay. So that will create some problem to handle the approximation. Lagrangian की beauty क्या है कि it will provide order better accuracy, but if you improve more degree, that will create a problem computationally. You suppose degree of approximation for polynomial degree 10 you want to find by Lagrangian, that's fine. But you improve the degree of 100 and you approximate by Lagrangian, it will create problem due to computational problem. If computational is efficient, if your machine is efficient, we can think. But definitely there is limitation due to Lagrangian. Okay. So yeah, we can do. There is my student is working on scheme one. L1 2 3 sigma is there. L1 2 3. So we just going to do reverse 3 to 1 sigma something. So we set up this. Order is improved.
At the same time, the computation cost will be reduced.
Yeah. Yes. That is major task when you do approximation. Yeah, your machine is not good enough, then program को run कराएंगे मालूम हुआ सुबह तक कुछ आए नहीं. So there is maybe one, yeah.
The calculation of that, so let's say from linear to non-linear.
Yeah.
Directly you can approach, or you have to again go for some.
No, we are not doing linearization. We just going to direct. We have implemented for non-linear case as well. We submitted this.
Same Lagrangian concept.
Yeah, same Lagrangian concept we have implemented. We just use Taylor series extension of that non-linear and then implement it. It's working. And we have changed the mesh as well. We have chosen the mesh, graded mesh, as well as adaptive meshes. And in both cases, the method is working for smooth data.
So one thing you can do, just my suggestion, you have done the now linear, so go for semi-linear.
Yeah.
Then quasi-linear, then I-linear.
Yeah.
So one step. So I think semi-linear.
Yeah, already done. For non-linear case, we have done. Yeah, we have done for non-linear case. For non-linear case, we have submitted one paper.
Submitted.
Yeah,
not here.
Yeah,
not so. That's why I asked you. You don't want to sue us.
But in the future, I told we have.
Yeah. It's okay. So congratulations. Huh?
Thank you.
Yes.
Yeah.
Yes.
Yeah.
The party is there.
You have considered the differential equation in the fractional derivative sense. Generally, in the dynamics heat transfer, when we are considering the heat equation or diffusion equation, both are almost only the terms are different. So how will maintain the dimensional homogeneity? Because left hand is your fractional derivatives, and the right hand is the second order derivatives. So when we talk about the particular parameters, so in the sense of physics, mathematics is good, fine, but how will handle? Because dimensional homogeneity will not follow. In mathematics point of view, it is fine.
Their homogeneity is not there. I agree. Because their dimension is 0, 1, between 0, 1 and there is 2. So
when it is 1, then it is fine. But when in between 0 to 1, and even if it is 0, then again it will not be the diffusion equation.
There is 0, 0. They strictly get away. Yes. But okay, I agree with you. That's why given the geometrical interpretation, if you use d by dx for x square, initially I discussed with the students, with all faculty members, that if you differentiate like x square by d by dx integer order, you will get to straight line. But we are not getting straight line directly. In between there is a story. There is a history. So d by dx is working as an operator. Like suppose if you implementing some force, bend curve hai, then you getting it as a straight line. So there is some intermediate step. That step we can cover through fractional derivative. In the same sense, in the fractional diffusion model also, the intermediate information we can capture. Only. That is the only beauty of that.
He is raising the question of unity.
Yeah.
EAC.
Unit. Yeah, I agree.
No,
Yeah.
that is the problem is there. Another problem
The
is
dimension is related to dimension.
Not
Also, I
only
got your
dimension,
point.
parameter also. That is
Yeah.
sort of things. Another thing is that okay, geometrically it is fine, but still physically it is not okay. Justified. That is what basically fractional differential equation. Okay, physically means okay when I am dealing with the diffusion equation, because we have seen that mathematically it is giving good results. That is fine. But what exactly it is meaning? Because still now that is also not.
Yeah, that's
not
we say not this. We are simply as a numerical analysis. We are just developing the
mathematically
scheme.
it is
But in point of physical point of
but
view,
another
I
point
have
is
one.
that it is non-local. That is another issue.
Yeah, non-local operator.
So
The
that is another
hereditary
issue. When
properties.
you have some sort of new non-homogeneity
Yeah.
in your system, it is difficult.
This is a non-local operator.
That's what I'm telling.
Yeah.
But many times in physical scenario, you have a local local solution or
Yes.
locally okay. That means
That's why there is a operator to them, local and non-local.
Lot of issues are there.
Yeah, no, that is fine.
But mathematically it is fine. But we have seen that solution is good.
But no, not only solution. We can find many behavior. I told you the like simple. I give an example for x square case. We can find the behavior how the shape is changing. The intermediate state. That information you cannot capture by integer order directly. You don't know how this picture will come from x square to x. x square को differentiate करेंगे तो straight line आएगा. So that curve is not going directly there. There is some steps. That in step in how the shape will come. That structure we can find out.
Even in the material science, what we are thinking, the changes or transformation from one state to another state, like solid to liquid, liquid to gases, there is a transformation,
Yes.
but still we are thinking that how will relate, and the fractional models are there for the viscoelastic fluid. But how we can control the dimension of
That is
the
the problem.
transformation,
I agree.
it is very much
Yes.
challenging
Yeah,
for all people. I will
But
just say
definitely
that
one day this problem will crack, and that how it will come, the dimension issue will be.
Now, you see, initially it was started by the mathematicians. Now, a number of people from engineering, they are showing their interest and doing works. So that is the success. And eventually all the questions will be.
But that's sir, I believe if you really happy with your
Yeah.
mathematics, then you should not also worry about always application as a numerical analysis. So I am happy with my analysis part. That, okay, I am doing something, I am getting mathematically correct. So okay, let them other will do application. But okay, it's fine. Your question is correct.
सर एक चीज और हम जानना चाह रहे हैं तो ये सिर्फ डिस्कस हुआ सर जैसे ये डिफ्यूजन इक्वेशन था फिक्स लॉ से गवर्न है तो जो डिफ्यूजन केस में अगर हम लोग उधर फ्रैक्शनल डेरिवेटिव यूज कर रहे हैं तो सुपर डिफ्यूजन या सब डिफ्यूजन का केस है ठीक तो ये फ्रैक्शनल डेरिवेटिव में जो सुपर डिफ्यूजन या सब डिफ्यूजन है वो एक केस ना हो के वो कई इंटरमीडिएट स्टेट को ज्वाइंटली सुपर डिफ्यूजन या सब डिफ्यूजन यूज कर रहे हैं
then again the interface problem will be there. How you will control the interfaces between
Problem is dimension is different, so handling is difficult.
Just I want to add. Suppose a linear equation is there. Del alpha u by del t alpha plus something. Then you can say for alpha greater than 1, it is a super diffusion, alpha less than 1, subdiffusion, alpha equals standard diffusion. But non-linear, it may not be alpha greater than 1, even started from alpha less than 1, because non-linearity effect is there. So subdiffusion and superdiffusion in non-linearity is a bad term, not properly used in what is used in fractional derivative in linear cases. So those are also the intermediate stage. So intermediate stage is very important.
And in this case, one more question is there. For the young, because he is my friend, I am not interested to ask any question.
ये तो डिस्कशन है ये तो होनी चाहिए इससे हम लोग
when we are defining the linearity of the differential equation, so basically we are calculating the degree of the terms derivative and the dependent variable. In that sense, degree, the definition of the degree is it is free from the radicals and fraction. Okay. So when we are talking about the linearity or non-linear of the fractional differential equation, how we'll handle this thing? Because we have to first reduce or free from the radicals and the fractions, and then how we'll define the linear or non-linear fractional differential equation. Got
got your point.
मीन्स नॉन लिनियरिटी का सेंस है भी या नहीं फ्रैक्शनल में यही प्राइम क्वेश्चन हो गया
How will define?
So those things are okay. All
Is it
open to you.
even if it may be meaningless to talk about null identity as
That's
far as
correct.
fractional is
If
concerned.
defining the linearity, that should be fraction. Whenever you're defining the order, that order whatever we have, it should be fraction. But itself, it is fraction.
Before ending, just I want to give a overview. What he has raised in intermediate. Suppose हम लोग ये करते हैं ना जो इलास्टिसिटी माने मेकेनिक्स में क्या बोलते हैं जस्ट इसको सब्जेक्ट ना एक मिनट जस्ट
हम लोग हैं सबमिट
ये अच्छा स्टोरी है क्या बोलता है सबसोनिक सबसोनिक प्रोपगेशन तो सुपरसोनिक
सबसोनिक
इलास्टोप्लास्टिक रीजन में जाते हैं तो आई वाज डूइंग रिसर्च दैट टाइम 90s अभी तो बुढ़ा हो गया साल पहले रिसर्च तो हमारा जो गुरुदेव माने जिसके पास पीएचडी किया वो अपने को आइंस्टाइन न्यूटन का नीचे सोचते नहीं है तो यस इट इज वेरी इगोइस्ट पर्सन so he used to say why the graph is coming is तुम इसका बीच में करो रिसर्च देखो कैसे होता है इसका बीच में why it is coming this why is coming और हम तो घर आके बहुत गाली देते थे ये बुआ हमको छोड़ेगा नहीं लग रहा है ये इससे काम कराएगा इससे रिसर्च फालतू है हैं ये फालतू आदमी का पास घुस दिया था एंड लेट यू नो वो जो ग्राफ हुआ था दैट इज गोइंग फ्रॉम सबसोनिक टू द supersonic. That paper was published in a very highly reputed journal, Engineering Fracture Mechanics, which was been 2 times referred in the journal Nature. Nature में reference हुआ था 2 बार. So sometimes it happens that this is the research. This is the research. You don't know what will happen tomorrow. So you have to work hard. You the young people, you have to work hard for it, and you will get result. Because research देता है कुछ ना कुछ. कम से कम अच्छा नौकरी तो देता है
अदरवाइज अगर आपको अच्छा लगता है
अच्छा लगा तो वो
थैंक यू
नेक्स्ट नेक्स्ट कैंडिडेट नेक्स्ट इज इनवाइटेड द बिजनेस संजू तिवारी contribution not written. Go for Vineet Singh. No, I will. You have to introduce myself. You are from where, madam? I am from Sarda University. So it was manner to introduce herself. Okay. And now start. What is your area of research, madam?
My area is knowledge graph and semantic web. Yeah.
Discuss the things in one platform. Huh?
Yeah. So I need to come here.